From 10.3, this is number 21, and your directions were to replace the polar equation by an equivalent Cartesian or rectangular equation, and then identify or describe the graph. Well, this was our polar equation. So what we can do is we can rewrite this as 4 over, remember this cosecant is 1 over the sine of x, and we've got our conversions that y equals our sine of theta. Oh, sorry, 4 over the sine of theta, excuse me. 4 cosecant of theta is the same thing as 4 over the sine of theta. But we know that y equals r sine of theta, so if I multiply both sides by the sine of theta, I've got r sine of theta equals 4. But this is the same thing as y, so I can write y equals 4, and that's just a horizontal line. So I always want to get these things in terms of remember these conversions from number 1, cosine, x equals r cosine of theta, y equals r sine of theta, tangent of theta equals y over x, and r squared equals x squared plus y squared. So we're going to use these conversions to get us from polar to rectangular, polar to rectangular, polar to rectangular, polar to rectangular, and polar to rectangular. Okay? We're back and forth. On number 23, this was the equation r cosine of theta plus r sine of theta equals 1. Well, we know that this is going to be x, and this is going to be y. That's right from our conversion, so we just say x plus y equals 1. If I solve for y equals negative x plus 1, so this is just a straight line. The slope is negative 1, and the intercept is 1. Okay? And number 25, r equals 5 over the sine of theta minus 2 cosine of theta. So what I could do is I could just multiply both sides by the denominator. Okay? And then I can multiply it, distribute out, so I get r sine of theta. And then 2r cosine of theta equals 5. And this is just going to be y. And this is going to be x, so I just get y minus 2x equals 5. Solve for y, and y equals 2x plus 5. That's a line whose slope is 2 and whose intercept is 5. Or goes to the point 0.05. Okay? And 27. These aren't too bad once you get the hang of them. There's some tricky ones, but these are fairly stable. Now, this is cosine squared of theta equals sine squared of theta. Now, this is funny because usually we can't multiply both sides by a variable because it might be 0, but r is a radial segment, and it's always going to be greater than 0. Otherwise, it's a trivial case. So we can just multiply both sides by r squared. I always feel a little funny doing this, but it's legal in polar coordinates. Once we do that, we can rewrite this as r cosine of theta squared and r sine of theta squared, just by using our properties of exponents. But this is the same thing as x, so it's going to be x squared, and this is the same thing as y, it's going to be y squared. So I get x squared equals y squared, or y equals plus or minus x. Well, if we think of this, y equals plus or minus x, this is just a straight line, y equals x, this is a diagonal line. Y equals x, and y equals negative x. That should be negative x, not negative 1, pardon me. Let me fix that right now. So hopefully that makes sense. These aren't too difficult. Y equals positive x, and y equals a negative x. There we go. Okay. And number 29, r equals 8 sine of theta. So this is another one where you just multiply both sides by r, and like I say, it seems a little odd because we normally don't allow that because r might be 0. But in this case, r won't be 0 because it's a radial segment, so I multiply both sides by r, so I get r squared equals 8r sine of theta. Now, r sine of theta is y, and r squared, remember, r squared equals x squared plus y squared. Y equals r sine of theta. So this just becomes x squared plus y squared equals 8y. And then we can subtract 8y from both sides. We can add 4 to both sides, and we'll get a complete square. So now we have this in the form of a circle. X squared plus y minus 4 squared equals 4 squared, and that's a circle. The center is at 0, 4, and the radius is 4. So that's what we've got. So those aren't too bad.